Assalamu alaikum everyone. In this video tutorial, we're going to talk about a really important topic in engineering thermodynamics, and that topic is the calculation of heat of reaction. So before we learn about these processes of the calculation of heat of reaction, first of all, we should know what heat of reaction is, right? So basically, when any chemical reaction takes place, heat is either emitted in the environment or heat is absorbed from the environment. So the amount of heat that has been emitted in the environment or absorbed from the environment, that's called the heat of reaction. If we look at this part of the slide, we can see that there is a chemical reaction here, and there is a certain amount of heat or a certain amount of enthalpy, if I say specifically, that has been indicated here. So what does this amount of enthalpy signify? Basically, if this was a box in which the chemical reaction was taking place, not necessarily it has to be a 100% conversion, it might be a 70% conversion or a 50% conversion, that doesn't matter. So after the completion of one chemical reaction, 1 moles of the products and 1 moles of the products form something of the reactants, then the amount of heat absorbed from the environment is going to be 41.16 kilojoules. So this is an important thing. With the positive term, I have associated the absorption from environment. Okay, so absorption from environment. So evidently, with the negative term, we're going to associate what? In the negative term, we're going to associate that the heat is being emitted into the environment. Okay, so with the positive term, we associate absorption of heat from environment, and with the negative term, we associate the emission of heat from environment. So basically, if this delta H was negative 41.16 joule, I'm saying basically, if supposedly, if this value was negative 41.16 joule, then we would have to say it like that after the completion of this chemical reaction, whatever percentage of conversion it may be, 41.16 kilojoules of heat is going to be emitted into the environment. Emitted into the environment. Okay, so this is basically the heat of reaction. After the completion of a chemical reaction, there is going to be some amount of heat that has been absorbed from the environment or some amount of heat that has been emitted into the environment. Okay, so we're going to calculate how much heat is going to be absorbed from the environment or how much heat is going to be emitted from the environment. So basically how we're going to do it. In order to calculate the heat of reaction, we need to familiarize ourselves with another term like the heat of formation. So basically let's concentrate here. What is the heat of formation? Okay, so now we're going to talk about the heat of formation. So basically what the heat of formation is. Okay, so heat of formation, this is the chemical reaction in which a compound is formed from its elemental components. For example, if I talk about carbon dioxide is a gaseous molecule, right? Carbon dioxide is basically a gaseous molecule. So what I'm going to write for the heat of formation of carbon dioxide, the reaction is going to be that the carbon solid and oxygen gaseous, these two components react, and then they produce carbon dioxide in a gaseous state. So this is going to be the heat of formation reaction for carbon dioxide, heat of formation for carbon dioxide. Similarly, for water, a really familiar molecule for our cells. So what we are going to say about water, we can familiarize with ourselves with this chemical reaction. I am pretty sure that many of the viewers here already know this chemical reaction, that the combination of hydrogen and oxygen produces water. And here's going to be a half here because of the moles of oxygen present in the water molecules. Okay, so basically this is the heat of formation reaction for water. Okay, so with this concept, we're going to calculate the heat of reaction. Okay, with this concept, we're going to calculate the heat of reaction. So how are we going to calculate the heat of reaction for any chemical reaction using this heat of formation reactions? Let me uh, let me show you that. So basically let us go back to that example, that carbon dioxide and hydrogen, they are reacting and they are producing carbon monoxide and water in the products. So if we think about this reaction, let us consider each of the compounds. Okay, so first of all, let's consider carbon dioxide. Okay, so for carbon dioxide, so this is a reaction that carbon dioxide gas and hydrogen gas, these two gases are reacting to form carbon monoxide and water. This reaction has a particular name. The name of this reaction is water gas shift reaction. Okay, the name of this particular reaction is water gas shift reaction. It is a important fun fact to remember. And then so carbon dioxide and hydrogen gas is reacting to form carbon monoxide and water. So basically, for carbon dioxide, if we think about carbon dioxide, we have just wrote the heat of formation reaction of carbon dioxide, which is that carbon dioxide is a gaseous molecule which gets formed by carbon and oxygen, the reaction between carbon and oxygen. And here now, notice that I have written this reaction in the opposite way than I have written before. Why did I write this reaction in the opposite way? It's because that carbon dioxide is in the reactant part of this chemical reaction. So as carbon dioxide is the reactant part in this chemical reaction, that's why I have written the heat of formation reaction for carbon dioxide in reverse. Okay, so the molecules that are present in the reactant part, we're going to write the heat of formation reactions in the reversed order, and the molecules that are present in the product, we're going to write the heat of formation reaction in such a way that these respective molecules be present in the product. Okay, let me show you what I mean by that. So first of all, we have wrote for carbon dioxide, and then we're going to write about hydrogen gas. But the problem is hydrogen gas is already a diatomic molecule. So the reaction, heat of formation reaction for hydrogen gas, it doesn't need to be it doesn't need to be attended. Okay, so now we're going to shift our attention to carbon monoxide. So basically, the formation reaction for carbon monoxide can be similarly, it is also the reaction between carbon and oxygen, but here the oxygen is not going to react in its full molar composition. So what's going to happen here, carbon solid and half moles of oxygen in its gaseous state are going to react to form gaseous carbon monoxide. Okay, and then the water, the heat of formation reaction for water, we have already seen that hydrogen gas, the combination of hydrogen gas and oxygen gas, so these two react and form the water molecule. Okay, so let me tell you a reminder. In the heat of reaction or the calculation of heat of formation, the states of the products or the reactants is really important. The heat of reaction values entirely dependent. The heat of reaction values is entirely dependent on the states of the reactants or the products. So it's really important to mention the states of the heat of the reactants and the products. Okay. Okay. So now we're going to sum up the whole reaction. Then there comes a question that how can we sum up the whole reaction? It's like the heat of formation reactions. So for okay, so how can we sum up all these three reactions? So we have gotten so far three reactions, three heat of formation reactions for this entire reaction, for the entire actual reaction that we are going to calculate the heat of reaction for. So in the first reaction, we're going to get a value of heat of formation. For the second reaction, we're going to get another value of heat of formation. And for the third reaction, we're going to get a third value of heat of formation. So now let me tell you a very important characteristic of enthalpy. Enthalpy is a state function. It doesn't depend upon the path that you take in order to get from your initial state to your final state. Okay, so enthalpy is basically a state function, and a state function does not depend upon the path. So basically, if I wanted to go from point A to point B, if I wanted to go from point A to point B, if it was a state function, if my path was a state function, then it wouldn't depend on which path I take. If I took this path, or if I took a straight path, or if I took a circular path, semicircular path, it wouldn't depend. The answer would always be the difference between the initial and the final value of my state. Okay, so enthalpy is almost like that state. Enthalpy is like the enthalpy only depends upon the final state and the initial state of your reaction. So the it doesn't matter if I calculate the heat of reaction through these heat of formation reactions. It only depends upon the initial and final reaction. So if I manage to get the final reaction, or if I manage to get the final products with the combination of infinitely amount of heat of formation reactions, it would not depend, it would not vary with the heat of formation combinations. Okay, so that's why I can add up these heat of formation reactions in order to get my actual reaction. Okay, so now if we add up these reactions, let's see. First of all, carbon dioxide in the reactant part, we're going to write carbon dioxide in the reactant part. And then there is carbon solid in the product part. Now please pay attention here. Carbon solid in the product part is produced, let's say, in 1 moles. So now if we look at the second reaction, carbon solid, the amount of carbon solid produced in the first reaction is being exhausted in the second reaction. Okay, so we can't write carbon solid inside the total reaction. Okay, so now let's look at oxygen. Oxygen is produced in 1 mole, right? 1 mole oxygen is produced in the first reaction. So now if you look at the second and the third reaction, half moles of oxygen is being exhausted in the second reaction and half moles of oxygen is being exhausted in the third reaction. So the total amount of oxygen that has been produced in the first reaction has been exhausted by the second and the third reactions. So we can't write oxygen either. Okay, now if we look at the rest of the reactants and products, in the product part from the second reaction, there is carbon monoxide, which is not being exhausted in any other part. So we're going to write carbon monoxide in the product part. And also in the product part, there is hydrogen. In the reactant part, there is hydrogen gas, which is not being exhausted in any other reactions. So we can write hydrogen gas in the reaction part. And then in the product part, there is also water, which is not being used in any other reactions. So we're going to write water. So see, from the combination of these three heat of formation reactions, we have finally obtained our actual reaction. So if we now try to calculate the heat of reaction for this one, we can just add up the heat of formations for the above reactions, and then I would get the heat of reaction. So this is the method we will use for so this is the method we're going to use for calculating heat of reaction for any chemical reaction. Let us go through the first example here. The example states that calculate the standard heat of reaction at 25 degrees Celsius for the following reaction. Okay, so there is a chemical reaction here, and it has the question demands that we calculate the standard heat of reaction at 25 degrees Celsius. So there is an important, very important piece of knowledge here. At 25 degrees Celsius, the reaction is known as the standard heat of reaction. Okay, so always remember the standard conditions for our heat of reactions is at 25 degrees Celsius, and the pressure is always atmospheric pressure, and if the pressure is anything else, then it will be mentioned in the question, and it will affect our heat of reaction in some other way, which we will discuss later. So basically in the standard state, the heat of reaction, the standard state is 25 degrees Celsius. Any other temperature or any other pressure is going to be other than standard state. Is not going to be a standard state. Basically it's not going to be a standard state. Okay, so the heat of reaction at 25 degrees Celsius is known as the standard heat of reaction. So it has told us to calculate the standard heat of reaction. Okay, so if we write the corresponding heat of formation reactions, the total heat of reaction directly for the heat of reaction, for the calculation of the heat of reaction, we're going to always use output minus input. Okay, so if we look at this heat of reaction, if we look at this heat of reaction, so there in the output there is a water molecule and there is chlorine molecule, but the chlorine molecule is a diatomic molecule, so the chlorine molecule is not going to be included in the heat of formation. The water molecule is going to be included, so the heat of formation for water molecule, and notice that the water molecule has a stoichiometric ratio 2 before it. So in order to fully include the heat of formation enthalpy of the water molecule, we need to multiply this by 2 because of the stoichiometric ratio, and then we're going to add a negative and then the negative input. So what is going to be in the inside the input? So inside the input there's oxygen, which is basically a diatomic molecule, so it's not going to be included in our heat of formation calculation. And there is hydrochloric acid, so we're going to add the heat of formation for hydrochloric acid, and we're also going to multiply it by 4 due to the stoichiometric ratio. Okay, so basically this is our heat of reaction method, and now the question arises that how we are going to obtain the heat of formation values for the water molecule and for the hydrochloric acid molecule. So we're using the data from Smith book, uh, this book, Chemical Engineering Thermodynamics by Smith, J.M. Smith, and Abbott and Van Ness. So this one has a data booklet inside it. This one has a table of data inside it, and at the table of A, sorry, at the table of C. I'm okay. So at the table of C1 and C2, from table C1 to table C4, the information is given here. All the heat of formation reactions for various substances are given in this book. So we're going to use the informations that are provided here in this book. So from this book, we can see that the heat of formation for hydrochloric acid, the heat of formation for hydrochloric acid is minus 92.3 kilojoules, and the heat of formation for water molecule is minus 241.818. Okay, so and also be careful, the water molecule can be in gaseous state or the water molecule can be in uh, liquid state. So you have to be very careful in which state the water molecule is in. If it's in the gaseous state, then the heat of formation value is going to be 241.818, but if it's in the liquid state, the heat of formation value is going to change. So by calculating this part, we can easily determine the heat of reaction, the total heat of reaction for this chemical reaction. Okay, and also disclaimer, I would like to admit a mistake that I have made. The heat of reaction, this one, the heat of reaction, this one is going to be a little bit different. See, we have written the reaction of carbon dioxide. We have written the reaction of carbon dioxide in the reverse order. So mainly the heat of formation reactions is calculated for the formation of carbon dioxide. But in this reaction, we have written the chemical reaction in the reverse order. So there is going to be a negative in front of it, and similarly there is going to be a negative in front of it. That's why we do output minus input, because see, the reaction for the products, the formation reaction for the products is in the normal condition, like the carbon monoxide and water molecule is being formed by the reaction of hydrogen and oxygen gas. But in the first reaction, carbon dioxide, it's the reverse reaction of the actual heat of formation reaction. Okay, so that's why we always need to do output minus input in case of calculating heat of reaction. Okay, so bear that in mind and correct this in your notes. Okay, so I think we are oh, pretty equipped with knowledge about calculating the heat of reaction in the standard condition, right? For the standard condition, we just simply determine the heat of reaction equation through the values of heat of formation. Look up the values from the book of Smith in the table C1 to C4. Basically in table C4, the heat of formation values are given. So include those values in the equation, and then bam, you get your heat of reaction value. Okay, so in the next video we're going to talk about how to calculate heat of reaction in conditions other than the standard reaction. Okay, until then, uh, stay tuned and enjoy learning. Okay, assalamu alaikum.